Welcome to our series on Anchored Causality Theory. Today, in Lecture 1, we're going to slow down and really look at why quantum mechanics presents such a profound dilemma for our understanding of reality. Anchored Causality Theory starts by addressing the strangest thing, the measurement problem. It's the gap between our math and what we actually see. We often hear that quantum mechanics is successful, but successful is an understatement. Its predictions are accurate to 12 decimal places. That level of precision is like measuring the distance between New York and Los Angeles to within the width of a single human hair. It's the most accurate theory we've ever had. Because of this accuracy, we've built our entire modern world on it, from the chemistry of your medicine to the GPS in your phone and the MRI in your hospital. But here is the hidden crisis. Despite these triumphs, the theory provides no mechanical explanation for how a measurement actually occurs. It tells us the probability of an outcome, but it never explains the physical process that turns a world of possibilities into a single concrete result. To see this dilemma clearly, we must look at the double-slit experiment. This is where Richard Feynman said the only mystery of quantum mechanics resides. Imagine firing tiny particles like marbles at a barrier with two slits. If we open just one, they pass through and form a simple clump on the back wall. But when we open both slits, something impossible happens. Instead of two clumps, we see an interference pattern, many stripes, just like waves in a pond. If we assume light is a particle, this means each individual particle somehow passes through both slits at once, interfering with itself. It's acting like a wave of probability rather than a simple thing in space. The real mystery is when we try to watch it. If we place a detector to see which slit the particle actually goes through, the wave behavior vanishes. It goes back to acting like a marble. The act of measurement itself seems to force the universe to choose, but how? The theory doesn't say, it just says the wave collapses. This led Erwin Schrödinger to propose his famous cat experiment. He wasn't trying to show how weird the world is, he was trying to show how absurd the theory had become. He imagined a cat in a box with a radioactive source. If a single atom decays, a quantum event, the Geiger counter triggers a hammer that breaks a flask of poison. According to the math, until we open that box, the atom is both decayed and not decayed. Therefore, the cat is both alive and dead at the same time. Schrödinger's point was that this is clearly ridiculous. We don't see half-dead cats in the real world. Something is missing from the theory. This is the and/or problem. The math says and, both states exist, but our experience always says or, it's one or the other. How does the and become or? Some physicists say, shut up and calculate. And why not? The math works brilliantly. But without a mechanical theory of measurement, we are using a powerful tool without fully understanding why it works. It's an engineering success, but a conceptual mystery. It's a conceptual hurdle that challenges our full mastery of the quantum realm. While we can build quantum computers today, we are doing so without a mechanical theory of measurement, navigating the terrain without a complete physical map. Let's look at the math one more time. We describe a quantum state as a vector, a sum of every possible outcome, each with its own amplitude. We use the Born rule to get probabilities, but we have to add it to the math by hand. It's a patch on a theory that is fundamentally incomplete. For over 100 years, from the Solvay conference in 1927 to today, we have accepted this spooky action because the math works, but we've stopped asking why. There is still no consensus. Every few decades, a new interpretation is proposed, but they all still leave the anchor of causality missing. Anchored causality theory offers a solution. We don't change the math, we change how we anchor the math to the physical events in space and time. In this series, we will prove that the spookiness is an illusion of our perspective. Waves are real and causality is anchored. Join us for Lecture 2.